Okay, so work done by spring we have done. Work done by spring, what is the formula? Minus k by 2 x2 square minus x1 square. Correct. Good. So during compression also same formula. Suppose this is the wall and this is the spring. Now this block is coming, so it will compress it. Now block has compressed it. So what is the compression? How much is compression? Suppose x. So what is the work done by spring? Again same formula we can use. Same formula you can use. So final compression is x. What is the initial compression when it is natural state? 0. So we'll write minus k by 2 x square minus 0 square. During compression also same formula. During elongation, same formula. During elongation, see, elongation means like this, you are holding this and you are moving it right side, so it is elongation, correct? Compression means, compression means you are holding here and moving it left. So spring is compressed. Are you getting? So spring is compressed. When spring is compressed, what is the work done by spring? Minus k by 2, final compression square minus initial compression square. Okay. So note down. During compression, if x1 is initial compression and x2 is final compression, x1 is initial compression, x2 is final compression. So same formula you can use, same formula. During elongation, what is the formula? Minus k by 2 x2 square minus x1 square. So during compression also same formula, okay? So minus k by 2 work done by spring is equal to minus k by 2 x2 square minus x1 square. So solve this question. Now K value I am giving 100 Newton per meter. This unit is clear. What is the unit of K? Newton per meter, because F is equal to Kx. So K is equal to F by X, Newton per meter. Okay, fine. Find work done by spring when compressed by 1 centimeter. What is the work done by spring when compressed by 1 centimeter? Okay, calculate. What is the work done by spring when it is compressed by 1 centimeter? So initially it is natural. Initially it is natural. Now you are holding the right hand and you are moving it left. So finally it is compressed. So how much you are compressing it? How much you are compressing it? 1 centimeter. So what is x1? 0. 0. Very good. What is x2? 1. So you will write formula, apply this formula. Minus k by 2 x2 square 1 centimeter. Now convert in meter. 10 raised to minus 2. So 10 raised to minus 2 square minus 0 square. So clear. So minus 50. 10 raised to minus 4 means, okay, 10 raised to minus 2 whole square is 10 raised to minus 4. So this is the answer. Okay, clear. So you can separate this 10 power minus 3. So you can write like this. So minus 50 into 10 raised to minus 1 into 10 raised to minus 3 joule, and 10 raised to minus 3 joule you can write millijoule, correct? Millijoule. And 10 power minus 1 10, it will become minus 5. So what is your answer? Minus 5 millijoule. Sometimes in option, in four options are there. Sometimes answers are given in joule, sometimes in millijoule. In joule, how much? In joule, tell me. Minus 5 by 1000. So minus 0.005 joule. Minus 0. Okay, understood. So you should be ready to find answer in millijoule, joule, both. Okay. Okay, fine. So 1 millijoule is equal to, tell me, 0.001 joule. Okay, clear. Okay, done. Now, next question. This is first question. Next question you solve. In above question, find work done by spring. Find work done by spring to compress it further by 1 centimeter. To compress it further, further means extra. Extra by 1 centimeter. To compress it further by 1 centimeter. Okay, solve. So what is the initial compression? 1. Initial compression 1. Okay, 1 centimeter you have already compressed. You have already compressed by 1 centimeter. Now extra 1 centimeter you are compressing. So what is final compression? Final. 2. Very good. Come to this. Come here. Now this is initial. So initially relaxed. Now relaxed. So what is the compression? 0. Now compressed. How much it is compressed? 1 centimeter. Okay. Now from here you are further compressing. So you are compressing like this. From here further you are compressing. So this is 1 centimeter, this is 1 centimeter. So what is the total compression? 2 centimeter. So for question number 2, what is x1? 1 centimeter. What is x2? 2 centimeter. Okay. Find work done. Find work done by spring to compress it further extra. Here to here you have already calculated. Okay, here to here, but here to here. Okay, now calculate. So what is the answer? Tell me. Minus k by 2. X2 square. What is x2? 4. 4 centimeter square. 4 into 10 power minus 4 minus 10 power minus 4. Correct? So this is minus 50 into 4 minus 1, 3. 3 into 10 is to minus 4. So minus 150 divided by 10,000. So it will be, tell me, 15 millijoule, correct? Minus 15 millijoule. Minus 15 millijoule. Okay. Are you getting? Calculation is also very important. Okay. Calculation. You have any problem in this calculation? Because okay, you answer this question. 10 power 3 into 10 power minus 4. What is this? 10 power minus 1. Very good. Now 10 power 7 divided by 10 power minus 3. How much is this? 10 power 10. Okay, 10 power minus 2 divided by 10 power minus 5. Tell me. 10 power 3, correct. Minus 2 plus 5, so 10 power 3. 10 power 3. Okay, yes. Here, minus 50 into 3. How we are getting? This 4 is there, 4. So, minus 100 by 2, 10 power minus 4 you take common. So, what you get? 4 minus 1. So, minus 50 into 10 raised to minus 4 into 3. Okay, clear? Common. Okay, done? Okay. Okay, see. So, this is a spring, work done by spring. And what is the work done by external? Minus of work done by spring. Remember this. External agent, work done by external agent, work done by external agent is minus of work done by spring. So suppose I am saying in above question, find work done by external agent to compress it further, then your answer will be positive. Okay, minus of this. Work done by spring is minus, so work done by external will be plus. Okay, because external agent is minus of work done by spring. So note down. Now next, see, suppose this is the ceiling and spring is connected. Initially it is relaxed. Now you connect a block. You connect block of mass m. It initially relaxed means what is the length? It is natural length. Natural length is L. Okay. Natural length L. Okay. So what is the spring force right now? What is the spring force right now? It is relaxed. So what is the spring force? 0, because elongation is 0. Elongation is 0. Right now no elongation, correct? Now this block you are holding and slowly you release it. Slowly you release like this. So the mg will pull it down. Mg will pull down. So the block will come down. So spring is elongated. Spring is elongated, correct or not? So spring force will be there. What is the direction of spring force? Up or down? It is elongated. So upward, very good. And mg is downward. So x is increasing. You are holding the block. Slowly you are moving it down. Like this, the block is there, and slowly you are moving it out. So x is increasing. X increasing. X is increasing. And when kx becomes equal to mg, when kx becomes equal to mg, the block will come to rest. Now it is at rest. So this is known as equilibrium. Equilibrium. What do you mean by equilibrium? Net force? 0. So what is the downward force? mg. Upward force? kx naught. Okay. So note down. So x naught is the x naught is the elongation in equilibrium. X naught is elongation in spring in equilibrium. Elongation in spring in equilibrium. So when equilibrium is there, so net force is 0. Net force is 0. So upward, downward equal. So kx naught is equal to mg. Okay, clear, done. So tell me, what is kx naught? Mg. So what is x naught? Mg by k. Mg by k. Okay, note down. Tell me. Okay. So Write down, write down. What I said, you just write down. Okay, note down. Uh, how many ends of a spring? How many ends? Two ends. One end is connected to ceiling. Okay, other end is connected to block. Okay, so initially spring is relaxed. Initially spring is relaxed. So relaxed means no elongation. Elongation is zero. Elongation is zero. Now block attached block attached to its lower end, block attached to its lower end is slowly allowed to come down, slowly allowed to come down. Like for example, very heavy object is there, very heavy object is there. uh, you are transferring from some height, you are putting some from some height to ground. So it is very precious object, like full of glass, correct? Glass is precious, precious in the sense, if it will fall, it will break glass. So I don't want it to break. So how you will help that person? One person is here, it want that glass object to come to ground. How you hold it? You hold like this, slowly, 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 slowly. You will put it here, correct or not? Like this, gently, slowly. So block attached to lower end of the spring, lower end of spring, and slowly allowed to come down. Slowly, slowly you are allowed to come down. So at one point it will come to rest. So you can remove your hand. You can remove your hand. Now it is not going up or down. So what is the downward force mg? Upward force kx. Okay. So balance. It is balance. So this is known as elongation, mg by k. Now it is at rest. It is at rest. Okay. Nothing is going on. If you want to further elongate it, you have to hold the block and pull it down. Then it will further elongate, extra elongate the spring. Okay. Further elongate. So mg can elongate only up to here. Weight, the weight mg can elongate from here to here, correct? Okay. And when it is slowly released, when it is released slowly, are you getting? Okay, when it is slowly coming, slowly it is coming down, then it will come to rest here. What if it is suddenly released? Suppose I am holding the block, suddenly released, what will happen? Then more elongation, more elongation. So we'll see. If block is released suddenly, note down. If block is released, if block is released suddenly, suddenly means like this. Uh, so this is gently released. I want this object to come down. So this is gentle. Okay. Now this is suddenly. Okay. Suddenly, just release. This is release. Okay. Clear? So block is suddenly released. Block is suddenly released. So what is the initial situation? Spring is there. This is the spring. So initially relaxed. Initially relaxed. Now you connect a block. So what is the elongation right now? 0. Now you are holding the block and release it. Suddenly it will come down. So spring will elongate more. Okay. Now block is here. So suppose elongation is x. So what is the upward force? Kx. Downward force mg. So kx is less. Kx is less than mg. So what is the direction of acceleration? Acceleration is where? Up or down? Downward. Acceleration is downward. So speed is increasing or decreasing? Speed increasing. Speed increasing. So speed increasing. But at one point, speed will become maximum. Now the block is here. The speed becomes maximum. When speed becomes maximum? When kx and mg are equal. Net force 0 means equilibrium. So in equilibrium, net force 0, so speed is maximum. After that, what happens? It will go down further. It will go down further. Now it is going down further, but speed is decreasing now. You tell me why? Why speed is decreasing now? Why speed is decreasing? Because what is the upward force? Kx, downward force mg. Which is greater now? Which is greater now? Okay, here which is greater? Here which is greater? Mg. Here both are equal because x is now more. X is more now, greater. Elongation is greater. But more greater, elongation is more greater. So which is greater now, kx or mg? Huh? Kx. Kx is greater than mg. So velocity is increasing or decreasing? Decreasing. Acceleration will be where? Up or down? Kx is greater. Acceleration will be up. Are you getting this point or not? See, let's take numerical. Let's take numerical value. Let's suppose k is equal to 10. K is equal to 10. M is equal to 1 kg. So, when x is equal to 1 centimeter, let's suppose x is equal to 1 centimeter. So, what is kx? 10 into 0.01. So, how much? 0.1. And how much is mg? 1 into 10. So, 10. Now, which is greater, kx or 10? Mg is greater. So, acceleration will be where? Down or up? Down, because mg is greater, correct? So, acceleration is downward, so velocity is increasing. Now, here velocity is maximum. So, what should be x naught? Tell me, what is the x naught value? Yes. Velocity is maximum because force is 0 here, net force 0. After that, which force is greater? When it crossed this point, after that, which force is greater? Kx is greater, correct? So, what is the direction of acceleration? Upward. So, velocity will start decreasing. Velocity will start decreasing. Are you getting? So, velocity will increase up to here. Up to velocity will increase. But after that, velocity will decrease. Okay, see, 0, like this, 0, like this. It is oscillating. It is oscillating. So, this is known as equilibrium. So, tell me, find out equilibrium, find out. So, x naught is equal to mg by k. K is how much? 10. K is 10. So, what is x naught value? 1 meter. 1 meter means you can say 100 centimeter. So, x naught is 100 centimeter. Now, x is more. X is more. So, kx is more. So, maybe x is equal to 2 meters, suppose, correct? Or 110, anything you can take, more than 100. More than 100 you can take 100 centimeters, suppose, okay? So, example. So, this will happen, understood? So, velocity decreasing, yes, yes. Velocity decreasing. So, ultimately, what is the velocity finally? After long time, what is the velocity? After long time, what is the velocity? 0. It will come to rest. It will come to rest. Note down. Velocity is 0. Okay, note down. So this block is released from here. How it is released? How it is released? Suddenly. You are holding the block, release it. So it will come down. It will come down like this. And final velocity again it is 0. So it is doing oscillation. It is doing oscillation. Okay, it is doing oscillation. Are you getting? Initial 0. Initially relaxed. The block, I am holding the block. So what is the initial velocity? 0. Now velocity is increasing. Velocity increasing. Up to what point velocity is increasing? Up to equilibrium. Up to equilibrium velocity maximum increasing up to this point. After that velocity is decreasing. Okay. Okay. Draw this diagram. Note down. Note down. Go through this question. Yes. Yes. Any problem? Tell me. Any doubt? Tell me. Tell me. Tell me. What? Zoom. Which part? This part? So spring is natural initially. Spring is natural initially. You are connecting a block. Listen, if you are everyone, so block is you are holding it connected. Now slowly you release it. Slowly you release it. So up to what distance it will come? Up to what distance it will come? X naught. And what is the value of X naught? Mg by k. Okay, and it will be at rest only. Now I am not disturbing. So it is at rest. Elongation is X naught, which is mg by k. Okay, now finish. What if you release suddenly? If you release suddenly, suddenly means like this, suddenly release. Okay, clear? Suddenly release. So the block will come down, come to rest. Again it will go up, come to rest. Okay, so it is oscillating. Okay, it is oscillating. So why it is oscillating? Why? Because initially which force is greater? Initially mg, then x is increasing, x increasing. So after some time kx and mg both are equal. Okay, but after that which is greater? Kx is greater. So at one point you can see the velocity is decreasing because acceleration is upward. So at one point velocity becomes 0. Okay, so velocity becomes 0. Now the question is, first you draw this. So here to here it is natural length, here to here natural length, and here to here is the elongation. So what is this elongation? We have to find maximum elongation. What is this maximum elongation? What is this maximum elongation? We have to find. Okay, understand it. See, spring is there. Okay, spring is there. It is connected here. You attach some object and release it. So what is the maximum elongation? Note down. Find maximum elongation in spring. Find maximum elongation in spring when block is released. Block is released suddenly. When block is released suddenly. So it is, once you understood this situation, okay, once you understand this, what is going on, then use the formula. Work energy theorem use. What is the work energy theorem? Change in kinetic energy is equal to total work done. So work-Energy theorem. So work done by spring plus work done by gravitation, work done by gravity, work done by gravity is equal to change in kinetic energy. Who is doing work here? Why this block is coming down? Why block is anything coming down? Why? Gravity. So gravity is doing work. Spring is also doing work. Positive work or negative work? Spring is doing positive work or negative work? Negative work. Very good. Spring is doing negative work because spring force is where? Upward. Displacement is where? Downward. So spring is doing negative work. Uh, Gravity is doing positive work. And what is the change in kinetic energy? Tell me. What is the final kinetic energy? Zero. Initial kinetic energy? Zero. So change in kinetic energy? Zero. Okay. Now you calculate work done by spring. Tell me. Spring work done minus K by 2 final elongation. What is final elongation? X max. X max square minus. What is the initial elongation? 0. And what is work done by gravity from here to here? Plus or minus? Work done by gravity plus. Very good. So plus mgh. And what is h? X max. Yes, yes. So mg into x max. This is the height. Suppose the block is falling. Suppose this is the block. It is falling by 1 meter. So what is the work done by gravity? What is the work done by gravity? It is falling by 1 meter. Force into displacement. Force is how much? Mg. Displacement how much? 1 meter. 1 meter. So what is the work done by gravity? Mg into 1. Correct? Now how much is displacement here? X max. So what is the work done by gravity? Mg into x max. That is equal to 0. Now take this term right side. So mg x max is equal to k by 2 x max square. Xm cancel. So mg is equal to k by 2 x max. So what is the formula for x max? 2 mg by k. Okay, note down. So when suddenly released, 2 mg by k. So when spring is released suddenly, when spring is released, spring is released suddenly. Yes, yes. Spring is released suddenly. Okay, like you have rubber band. Anyone rubber band? Rubber band. No one. Spring. Spring also you don't have. Uh, Physics lab is there, no? Not there. Okay, no problem. So spring is there. I don't know where to get spring. So market also shop. I don't know where. So suppose this is the spring. If you attach something here and you are holding it and slowly you move it. So slowly that object will come down and it will stay here. Spring is elongated, correct? Spring is elongated. This is the body. So this is known as slow elongation. Slow elongation. So what is the formula for that? How much elongation? Mg by k. Mg by k. In equilibrium, what is the elongation? Mg by k. So when spring is slowly elongated, what is the elongation? Mg by k. When it is suddenly released, when block is suddenly released, what is the elongation? Maximum 2 mg by k. Okay. Then yesterday we discussed one question. I am repeating that. Suppose this is the wall and this is the spring. Now this block is coming with velocity v naught. So what is the initial kinetic energy of block? Half m v naught square. And what is the initial elongation or compression in the spring? 0. Now block will come, it will compress the spring. So when compression is maximum, when compression is maximum, then what is the compression? What is the maximum compression? Suppose x naught. Maximum compression is x naught. So what is the velocity at that point? 0. So when block velocity is v naught, compression is 0. Compression is 0. And when block velocity is 0, compression is x naught. Compression is x naught. So how to find x naught? Suppose v is given to you. V is given to v naught. V naught is given to you. So use the formula. Work done by spring is equal to change in kinetic energy. Okay. Tell me what is work done by spring? Minus k by 2, very good, x2 square minus x1 square is equal to change in kinetic energy. What is final kinetic energy? Final kinetic energy 0 minus initial kinetic energy half m v naught square. Okay, so minus k by 2 x2 square, x2 is x naught, x2 is x naught, x1 is 0. Now this minus minus cancel. So k by 2 x naught square is equal to m by 2 v naught square. 2 to cancel. So what is x naught square? M by k into v naught square. So what is x naught? Square root m by k into v naught. Square root m by k into v naught. Okay, remember this. It is very important. Okay, so block is coming with speed. Block is coming with speed. It will compress the spring, and maximum compression is x naught. Okay, now you tell the block will be permanently here or it will go left. It will go left because spring again want to come to natural state. So spring will push the block. Spring will push the block left. Come. So it will push the block. Where it will push the block? Left side. Then again spring will come to natural state. Again spring will come to natural state. And where the block will move now? It will move left side. With what speed it will move? Same speed. We can find it. See, suppose it is going with V2. Now you see, now from here to here, you apply formula again. Work done by spring is equal to change in kinetic energy. So what is the work done by spring from here to here? Minus k by 2 into what is the final what is the final compression here now? 0. Good. It is natural state. The spring is natural state again. So final compression is 0. What is the initial compression? X naught. And x naught is this. Okay. Final kinetic energy half mv2 square. Initial kinetic energy 0. Okay. Here kinetic energy 0. So now minus k by 2 into minus x naught square. So x naught square is this m by k v naught square. M by k v naught square is equal to half m v2 square. So minus minus plus k cancel. So m by 2 v naught square is equal to m by 2 v2 square. M by 2 cancel. So what is v2? How much is v2? v2 is equal to v naught. Are you getting? v2 is equal to v naught. So The block is coming with velocity v naught. Block is coming with velocity v naught. It will compress the spring. Then again it will go left side with what speed? V naught. Are you getting or not? So what spring has changed? What spring has changed? Direction. Previously block is going where? Right side. Now block is going where? Left side. Okay. But no change in speed. Speed no change. Kinetic energy not lost. Kinetic energy not lost. Kinetic energy not lost. Are you getting? But here to here kinetic energy is lost. Here to here, kinetic energy is lost. What is the final kinetic energy here? 0. So where that kinetic energy is going? Potential energy. What you call it? Potential energy in spring. So that's why we use spring in suspension. Correct? So where do you use spring? Where do you use spring? You know, sofa. Why you feel comfortable more in sofa than this chair, plastic chair? Why? Because you know plastic chair is solid. Plastic chair is solid, correct? If you sit on it, the this surface is solid. It will not take your weight. But sofa, what is sofa? Sofa is like this. Sofa is like this, correct? So inside sofa, you open any old sofa is there. You open it, okay? You take scissors and open it. You will find so many springs. Have you seen springs? You will find why? Why a sofa has a spring? Why? Because if someone sit over it, the spring will compress. So you feel more relaxed, more comfortable. The solid surface is always pushing you up. Solid surface always pushing you up. So you are not feeling comfortable. But sofa means springs are compressed. Springs are compressed, so it is taking your weight. Springs are taking your weight, but it is not taking your weight. It is continuously exerting normal force. Okay, clear? So springs are used in suspension also. Springs are used in suspension also, truck suspension, car suspension. Okay, okay, fine. So, okay, so this we have done. Okay. Now let's solve one more question. It is given in your DC Pandey also. There is a block here and one spring you have connected here and one spring you have connected here. You have seen this question? Give me book, DC Pandey. So spring constant here is what? K1. Spring constant here, K2. So how many springs? How many springs? Two springs. So how many blocks? One block. So it is easy question. It is looking like two springs. One spring is very difficult to understand. Now we have two springs. Don't think like that. Springs are easy. Okay. Again and again you revise, you will understand it. So I will show you this question. Yeah, this question. 16. Page 347, question 16. So we will come to this. But before this, I want to explain this. What is going on here? So initially both springs are relaxed. So now you solve this. Tell me. Note down. Okay. So what type of surface is this? Smooth, frictionless. It is frictionless. Okay. Both are relaxed. Initially, both springs are relaxed. Relaxed means what is the compression or elongation? Zero. Very good. No compression, no elongation. Now you hit the block. You hit the block like this. Now block is hit. Block is hit horizontally. Hit horizontally to give velocity of v naught. Suppose you want to give velocity to some object, you have to hit it. Like for example, this object. What is the velocity right now? Zero. Now I will hit it like this. Correct? So what I have given? When you hit, what you have given? What you have given? Velocity. So you hit the block like this. So what velocity you are giving? V naught. Okay. So the question is, how much is the maximum compression in spring 2 and what is the maximum elongation in spring 1? Find maximum compression in spring 2 and maximum elongation in spring 1. Correct? What is the maximum compression? What do you think? The block is given velocity right side. So spring 2 compress or elongate? Spring 2 compress. What about spring 1? Elongate. Spring 1 elongate. It is connected here. Okay, it is welded. Welding is there. It is welded here. Okay, welded. So this is a question. So initially both springs are relaxed, natural state. Now block is hit horizontally to give velocity v naught, horizontal. Find maximum compression in spring 1, spring 2 and find maximum elongation in spring 1. So see what is going on here. These walls are fixed. These are known as fixed walls. Correct? So the distance between them is not changing, but the block is shifting right side. So now the block is here. When block is here, so if you look at this distance, so this is x, and this distance, this is also x. So spring 2 is compressed by x and spring 1 is elongated by x. Note down. Spring 1 is elongated. Spring 1 is elongated. Spring 1 is elongated by x and spring 2 is compressed by x. So, and what is the final kinetic energy? Maximum compression is there. What is the final kinetic energy? Tell me. Final velocity 0. Initial velocity v naught. So work done by spring 1 plus work done by spring 2 is equal to change in kinetic energy. Apply this. So this is work energy theorem. This is known as work energy theorem. Work energy theorem. Total work done is equal to change in kinetic energy. W total. So who is doing work here? Spring is doing work. How many springs? 2 springs. So spring 1, spring 2, both are doing work. WS1 plus WS2. Mg is doing any work? Mg normal. Displacement is horizontal. Mg is vertical. What is work done by mg? Tell me. 0. And what is work done by normal? 0. Both are 0. That's why I'm not writing. Okay. These both are 0. 0. This is also 0. This total 4. Total 4 forces. Okay. So these two are 0. So this plus this. Okay. Put the values. Put the values. So what is work done by spring 1? What is work done by spring 1? Work done by spring formula. Tell me. Minus k1 by 2. Very good. Final. Now spring 1, what is going on with spring 1? Elongation. So what is the final elongation? X. Very good. Initial elongation 0 plus again minus k2 by 2. Now compression. Final compression in spring 2. Final compression X. Initial compression 0. Like this you solve. Okay. So now that is equal to final kinetic energy 0, initial kinetic energy half m v naught square. So this is minus k1 by 2 x square minus k2 by 2 x square is equal to minus m by 2 v naught square. Clear? So minus 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 cancel. So k1 plus k2 by 2 into x square is equal to m by 2 into v naught. So 2 to cancel. So what is x? X square, tell me x square. 2 to cancel. So m by k1 plus k2 v naught square. So what is x? Square root m by k1 plus k2 into v naught. Clear? This is the x value. Are you getting? A single spring is there. Yesterday we did. Yesterday, so one spring is there. Block is coming with velocity v. What is the compression? Maximum compression. Tell me. Maximum compression. Yesterday we discussed. Minus k by 2 x square minus 0 square is equal to final kinetic energy minus initial kinetic energy. Tell me. So minus k by 2 x square is equal to minus m by 2 v square. Minus minus cancel, 2 to cancel. So what is x square? M by k into v square. So what is x? Root m by k into v, correct? Single spring. Single spring is there. So what is the maximum compression? Root m by k into v, correct? But two springs are there now. Now one left side, another right side, and these are fixed with the walls, these ends. Now this block is given velocity v. So this spring will get compressed, this spring will get elongate. So what is the elongation in this and compression in this? What is the formula? X is equal to square root m. Okay, m is there. Then instead of k, what you are getting? K1 plus K2. So they are acting like a series of parallel. Parallel, correct. Good. So we have discussed this. If springs are in series, if two springs are in series, so what is the equivalent spring constant? K1 plus K2. So parallel springs, okay, parallel springs, K1 plus K2. Same as capacitors, same as capacitors. If two capacitors in parallel, C1, C2, so what is the C equivalent? C1 plus C2. Okay. Okay, done. So now come to that question. So it is just reverse process. Now here what is the question? You are giving velocity and finally it is compressed. This is elongated. Now what is the question there? What is the 16 question? Page 347. What is the initial situation? Tell me, what is the initial situation? One of the spring is compressed, another spring is elongated. So how much is compression? X. What is the question? 16 question. Block of mass m attached to two unstretched springs of spring constant k. Both are k. Block is displaced towards right through distance x and released. The speed of the block when it passes through mean position. Mean position means this is known as mean position. This is known as mean position. What is mean position? When force is zero. Note down. Mean position means when force is zero, net force zero. When force is not there, that is known as mean position. This is also known as equilibrium. In equilibrium, you can say mean position. Okay. Mean position means force is zero. Now it is compressed by x. Now you release it. So again it will come back here. So when it comes to mean position, it will pick up speed. It will pick up speed. So same formula you can use. What is the formula for x? Tell me x formula. Root m by k1 plus k2 into v naught. So what is v naught? Root of k1 plus k2 by m into x. Now k1 and k2 both are equal. How much? K. Look at the question. Read the question. Two springs both have spring constant k. So what is the answer? Tell me. What is the answer? Correct. 2k by m into x. Okay. Square root 2k by m into x. Okay. Fine. Now 13 question we'll do. You have seen toy gun. Okay. Toy gun. This 13 question is toy gun. If I remove this word, if I remove this toy, now it is a gun. So gun, how fire? How fire gun? How do you fire gun? I'm holding a gun. How bullet will come out? Bullet. Again, physics and chemistry are there. Chemistry is there because chemical reaction is there. So suppose this is the bullet. This is the bullet, and trigger is there. Correct? You press the trigger. You press the trigger here. You press the trigger like this. When you press the trigger, what happens in the bullet? Some chemicals are there. They fire. Okay. Explosion happens. So when explosion happens, gases are released forward or backward? Backward. So gases are released backward. Okay, these are the gases are released backward. So bullet will be released where? Forward. So bullet will come out. Okay, so bullet will come out. Okay, understood? So physics is involved in this. Now it is a toy gun. In toy gun, you small kids are there. They don't use actual gun, right? They use toy gun, but concept is same. Physics is same. Something should be there to hit the bullet. Okay. So what is used in toy gun? Are you using chemicals? Explosions? You are using spring. Correct? You are using spring. So spring, how you are using spring? See. Suppose this is the spring. It is in natural state. It is a natural state. Now you put some ball here. Put some ball here and compress it. Now put some ball here. This ball is, so compression in the spring. What is the compression in the spring? X. You hold the ball like this and release it. So what will happen? Spring will push the ball right side. Again spring will become natural state and ball is not at rest. Ball will move with velocity v naught. So why? Why ball is going with velocity v naught? Why? Because the spring is doing work. So what is the work done by spring? What is the initial compression? X. What is the final compression? 0. So work done by spring is minus k by 2, final is 0, initial is x. So you solve this, minus minus plus. So what is the work done by spring? K by 2 x square is equal to change in kinetic energy. So what is the final kinetic energy? Half m v naught square. What is the initial kinetic energy? 0. So are you getting? Then you can find v naught. So k by 2 x square is equal to m by 2 v naught square. Correct? K by 2 x square. So v value you can find v naught is equal to square root k by m into x. But this is when you keep the gun horizontally. When you keep the gun horizontally like this. But in this question, read the question. 13 question. How you are keeping the gun? Gun is kept horizontal or vertical? Read the question. 13. A toy gun. 13 question. Huh. Read it, read it. We have to solve this. Toy gun uses spring of very large force constant. Force constant means K. Okay. K is very large. No problem. K is there. So very high value of K. No problem. If large value of K means V is more. So the ball will be fired with high speed. Correct? Suppose I will give you one example in police. Sometimes police use this toy gun also. Okay. Suppose large people are there, they are not control. Police is not able to control them. Large people, very okay. Something happened. Too many people came, but they are fighting. So police want to control the crowd. They don't use actual gun. Correct or not? They use a toy gun. Correct or not? They use toy gun. So the injury will be less. So in some countries, some Gulf countries, some problem was there. So they used a toy gun, but because with help of toy gun also, some people got serious injury. Okay, so some toy guns are also very dangerous. Correct or not? Okay, so let's solve the question. Toy gun uses spring force constant cage when charged before being triggered. This is known as triggered. Okay, you hold it like and release, triggered. Okay, so triggered. So now how you are holding the gun? Tell me. Triggered in the upward direction. What is the initial compression? X. If mass of shot means ball, mass of shot is m. How much height it will go? How much height it will go? Okay, so let's solve this question. So this is the spring. Now you want to put the ball here and compress the spring. So now spring is compressed and the ball is here. This is the ball. So right now, what is the velocity of ball? What is the velocity of ball right now? I am holding it like this. What is the velocity of ball? 0. And how much is compression? X. Compression is x. So I am holding the ball here. I am compressing the spring and release it. So spring force will act upward. So ball will go up. Okay. So question is, what is the height gained? How much height it will gain? So suppose it is going up to here. So x is small. x is small, x is small, okay. So from here to here, you can assume this is h. From here to here, you can use h. So from here to here, ball is going from here to here. What is the displacement? What is displacement? H. So who is doing work? Who is doing work? Which force is doing work? How many forces? Two forces, spring force and mg. Normal force not there. For normal force we need surface. Normal force we need surface. It is spring means spring force. So which force is doing work? So note down. Work done by spring plus work done by mg is equal to change in kinetic energy. So what is the final kinetic energy? At the topmost point, what is the kinetic energy? 0. What is the initial kinetic energy? Initial kinetic energy? 0. Final also 0. So 0 minus 0. Now what is the work done by spring? From here to here. Now spring comes to natural state. Spring comes to natural state. So what is the final compression? What is the final compression? Here to here. 0. Very good. What is initial compression? X. And what is the work done by mg? Mg is acting where? Downward. Displacement is where? Upward. So work done by mg plus or minus? Minus. So minus mgh. Minus mgh is equal to 0. Note down. So minus minus plus, so k by 2x square, you take this to the right side, is equal to mgh. So h is equal to kx square by 2mg, kx square by 2mg. Note down, kx square by 2mg. Okay, if you are finding this question difficult, let me give you easy question. So you solve one numerical. Let's come back to toy gun. Solve this numerical. Toy gun has spring of k is equal to 1000 Newton per meter. A shot means ball. A shot of mass 10 gram is used in it. Initially, spring is compressed. Initially, spring is compressed by 10 centimeter. Initially, spring is compressed by 10 centimeter. Find with what speed. Find with what speed the shot ball will come out of the gun. Shot ball will come out of the toy gun. Okay. From toy gun, with what speed it will come out? You know the direct formula also now. It is held horizontal. You know the direct formula. It is horizontal toy gun. You know the direct formula. Tell me. What is the direct formula? Okay, x you know. What is x? Root. Tell me direct formula. X is equal to root of m by k. Single spring. One spring is there. So what is V? How much is V? Root k by m into x. Okay, solve. One numerical is there. Okay. Which question is easy to solve? This one or the previous one? Question 2 or question 1? Question 2. Only one spring is there. So that formula also you know. I'm holding the toy gun like this. Spring is there. I'm putting the ball here. I will pull it like this. Spring is compressed. Now release it. It will fall there. Okay. It will fall there. Okay. So if you see in a village, people how they take fruit from tree. Fruit is there. Apple, uh, mango. So this is the mango. Okay. Now one student is there. How to take this mango without going there? You know that what you call it? I don't know. It is like this. There is a rubber here, rubber band, and you put one stone here. Correct or not? And do it like this. And do it like this. The stone will hit the mango here. Here, it will detach it. Mango will fall, and your another friend is standing below it. It will catch it. Okay. So same thing. So here rubber rubber band rubber band is acting like a spring. Okay. So toy gun is using a spring. Spring we can make in factory only, right? So in village factory is not there, so we are using rubber band. Okay. Okay, fine. How springs are made, that is not our study. Okay, so spring is made up of metal wire. Spring is metal wire given what type of shape? What type of shape? Spring has what type of shape? Spiral shape, or you can call helical shape. Okay, like this, helical shape. So tell me, what is the answer? Mass given. So K given. What is K? 1000. Mass is 10 gram. 10 into gram. Gram how much? Gram 10 power minus 3. X. What is X? How much compression? 10 centimeters. So 10 into 10 power minus 2. Now solve this. So this is solve this how much? Square root 10 power 6 by 10. This is 10 power minus 1. Square root 10 power 5. 10 power minus 1. Okay, so 10 power 5, how will you solve? 100 into 100 into 10 into 10 power minus 1. So 100 square root will be 10. So 10 into 10, then square root 10, then 1 by 10. Okay, this is 1 by 10. So 10 cancels. What is the answer? 10 root 10 meter per second. 10 root 10. 10 root 10. Root 10 approximately 3 point something. 3.14 you can take, because you know pi square you can take 10 approximately. Pi square is 10. So what is root 10? Pi value you know 3.14. So 3 into 10 into 3.14. So approximately what is the answer? 31.4 meter per second. 31.4 meter per second. Okay, are you getting? Okay, good. So note down. Okay, you have to revise it. Keep revising. Keep revising and memorize this formula. Okay, fine. Any more question? Actually, there are more questions. Okay, so no problem. We'll come back to spring later. Spring is finished. Now we will do next topic, potential energy. Write down. potential energy. What is the symbol for potential energy? U. Energy possessed by body due to bounded system. Bounded system. Particles may attract or repel. May attract or repel. Potential energy is associated. Potential energy is asso- associated. Okay, so what is potential energy? You understand the meaning of potential energy. Let's take example of charges. Suppose one positive charge and another positive charge is there. If you place one positive charge and near another positive charge, suppose plus 1 coulomb, plus 1 coulomb, so they will repel or attract? They will repel. They will repel, correct. So why they are repelling? Why they are repelling? So because it has energy. So initially they are kept like this. What is the speed? They are kept like this. What is the speed? 0. So no speed, but still they are repelling. So something is there. It is using that. That's why they are repelling each other. Okay. So when there is no use of speed, but still energy is there. Okay, like kinetic energy. You know what is kinetic energy? What is kinetic energy? Energy due to speed. When something is in motion, we say it has kinetic energy. Energy due to motion, speed, like car is there, bullet is there, okay, stone, ball, if ball is released from some height, ball is falling, so it has kinetic energy. So kinetic energy means energy due to motion. But what is potential energy? Potential energy is not due to motion. Potential energy is not due to motion. Potential energy is not due to motion. Then why? Then what is potential energy? It is not related to motion. Then what? So see, plus 1 coulomb, plus 1 coulomb. Right now I am holding it. So what speed is 0. But if you release it, they are pulling, they are they are pushing, they are pushing each other. So 1 coulomb will move right side, this 1 coulomb will move left side. So they are experiencing some force. So they are attaining speed. They are attaining speed, correct? So why? What was there before? When I am holding it, something is there in between them. That energy is known as potential energy. Okay. So it is like a hidden potential energy is something which is hidden. Directly what you can see, kinetic energy. If something is in motion, like fan is moving, rotating or translating, rotating. So rotating fan has what? Rotational kinetic energy, correct? Rotational rotational kinetic energy, correct? Suppose there is a cricket ball. Cricket ball you have seen. It is cricket ball. Okay, cricket ball is there. I am coming to you and giving to you. You will take it, correct or not? But suppose I am throwing it with very high speed. I am throwing the cricket ball with very high speed. You will take it? No, you will hide somewhere, correct or not? Because it is very heavy. You don't want injury. You don't want injury. It is very high speed. Mass is so much. Speed is also so much. You imagine mass is 1 kg. Mass is 1 kg. Calculate kinetic energy. Speed is say 10 meter per second. So 10 square. So how much energy it has? 50 joule. So something is coming towards you. You don't want to catch it because what energy it has? Kinetic energy. Okay, so kinetic energy is something which we can observe because it is related to motion. But Potential energy is not due to motion. We don't observe potential energy, but it is there. Okay. So like configuration. So this is known as configuration. System of charges. System of charges. So system of charges, how they are configured. Okay. How they are configured, like this is plus 1 coulomb, or this is plus 2 coulomb, or 3 charges are there, or 3 charges are there, or 4 charges are there, like this, 4 charges are there. So how they are configured? Configured means how they are placed. Configured means how particles are configured, means how they are placed, how they are placed, how they are placed. Okay. So suppose I am holding the pen here, I can catch it easily, I can catch it because height is less. But if I keep the pen very high, very far away, and now drop the pen, I will not catch it. Why? More height means which energy is more? See, if more height, if it is released from more height, okay, so what is more? Speed is more. What is the formula for speed? Root 2gs. I know if I release it from very large height, I will catch it. So speed will be more. Correct or not? So configuration is different. If you place it at less height, so configuration is different. If you place it at more height, configuration is different. Okay. So what is potential energy? What is potential energy? Tell me. Energy possessed. There is a definition given in your books. What is the definition given? Energy possessed. Energy possessed by a group of particles or particles. Energy possessed by a group of particles due to position and configuration. Position and configuration. Note down. So what is potential energy? Energy possessed by group of particles due to position and configuration. Position means where is the particle? Particle is here, 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 here. Like for example, this pen. This is ground, earth. This is earth, planet. The pen is here or here or here. Okay. So what is the position? And configuration means suppose 3 particles are there. How they are arranged? They are arranged in a line, or they are arranged like a triangle, or they are arranged like this. They are making a, what you say, 90-degree. Understood? So configuration means how they are arranged. Configuration means how these particles are arranged. Okay. So energy possessed due to position and configuration is known as potential energy. So kinetic energy, you know, it is due to motion, and position and configuration energy means potential energy. So there are some potential energy we are studying in physics. So what are the examples of potential energy? You know, gravitational potential energy. Second example, spring potential energy. Electrostatic potential energy. Magnetic potential energy. Magnets also have a potential energy. Magnetic potential energy, electric potential energy. Okay. Who stores magnetic potential energy? It is inductor. Inductor stores magnetic potential energy. Who stores electrostatic potential energy? You know, capacitors. Very good. Capacitor stores uh, electrostatic potential energy. Who stores spring potential energy? Clearly spring. Okay. Spring stores spring potential energy. Who stores gravitational potential energy? Mass. Mass particles like planets, Earth, Moon. What energy they have? Earth, Moon. Gravitational potential energy. Sun, Earth. What energy? Gravitational potential energy. North pole and south pole of magnet. Magnetic potential energy. Charges plus 1 coulomb and minus 1 coulomb. What energy they have? Electrostatic potential energy. Okay. Energy possessed by charges is electrostatic. Energy possessed by charges is electrostatic. Okay, clear? So in work power energy chapter, now we are not doing electrostatic, we are not doing magnetism. In work power energy, what energy we are going to learn? These two, gravitational and spring potential energy. Okay, so note down. So let's discuss the formula first. So before a formula, you understand this. Let's take very easy example. Let's take very easy example. Ball. Suppose this is the ball, mass of ball is m, this is the ground, this is the ground, okay. So initially the ball is here, initially the ball is on the ground, now you are taking the ball and you are putting it here. What height you are putting here? H. You are taking it to H. Slowly, slowly, see, ball is taken to, no doubt, height h. Ball is taken to height h slowly. Find external work done. How much external work done? Tell me. Find external work done. So when you are taking it slowly, so what is the downward force? Mg, and external force F. So this is external force, and what is the displacement? H. So now two forces are doing work. Two forces are doing work. So which force is doing positive work? Which is doing positive work? F or mg? F is doing positive work. So note down. So work done by F means external work done. External work done. So how much is external work done? How much is external work done? Fh. And F and mg same. F and mg same. So mgh. And what is work done by gravity? What is the work done by gravity? Minus mgh. Good. So when you are lifting something, when you are lifting something up, when you are lifting something up, gravity is doing negative work. Gravity is doing negative work. Like chair, I am lifting this chair. So gravity is doing negative work. I am doing positive work. So potential energy increases or decreases? When you lift something, potential energy increases or decreases? Hmm? Increases, correct. So potential energy increases. Potential energy increases. Suppose I will give one example. Okay, let's take practical example. Suppose there is a building. Suppose there is a building. There is a small kid and the big kid, or father or mother of this kid. Okay, this is kid and this is the father or mother of kid. Okay, so okay, fine. So this child is on the ground. Child is on the ground. So father or mother is happy. Okay, okay, child is playing on the ground. Now suddenly father or mother sees the kid is here. Kid is here. Terrace. Suddenly shock. Oh, what happened? So why why it is dangerous now? What is changed? The kid has more energy here, correct or not? Because if it is false, it will attain kinetic energy, it will hit the ground, correct or not? It is already on the ground, so energy is less. When on the ground energy is less, on the terrace energy is more. So what is that energy? Potential energy, gravitational potential energy. When mass object, when mass object is away, when mass object is away from earth, potential energy is more. Note down. So calculate the potential energy. So note down the formula. The symbol is U. So note down. Delta U is equal to external work done. Now I am giving formula. Okay. Note down. What is delta U? Change in potential energy. Change in potential energy is equal to W external, and W external can be written as minus of work done by gravity, because you know this example, work done by gravity is minus mgh. What is actual work done? Plus mgh. So remember this formula. So when external work done is positive, potential energy increases or decreases? When external work done, when W external is positive, potential energy increases or decreases? Delta U positive, so potential energy increases. And when external work done is negative, external work done is negative, delta U will be negative. So potential energy increases or decreases? Decreases. Okay. And one more point you write down. External work done is positive means work done by gravity is negative, and external work done negative means work done by gravity is positive. Okay. Suppose this object I am taking down. Object I am taking down. So work done by gravity is positive or negative? Positive. External work done? Negative. Okay, suppose this is the object. Mg is acting downward, F is acting upward. Displacement is downward. Displacement is downward. So Mg is doing positive work, F is doing negative work. So potential energy decreasing. So potential energy decreasing means external work done negative, gravity work done positive. Potential energy increasing means external work done positive, gravity work done negative. Okay, clear? Understood? Okay, so roughly little bit we have discussed about potential energy. Okay, so uh, let's so what is the unit of potential energy? It is joule. Okay, so solve. Note down. Ball is released from height 10 meter. Find gain or loss of potential energy. Find gain or loss of potential energy when it hits ground. Okay, answer this. When it hits ground, first you tell it is gain or loss. Loss. So delta U is positive or negative? Negative. So use the formula. What formula you will use? Delta U. What is delta U formula? Delta U formula means minus of work done by gravity. So ball is released from height h. So what is the work done by gravity? Plus mgh or minus mgh? Plus mgh. So ball mass you take 100 gram. Mass of the ball is 100 grams. 0.1 g is 10. Height is 10. So minus 10 joule. So work done by sorry plus 10 joule. So work done by gravity is plus 10 joule. Work done by gravity is plus 10 joule. So what is the delta U? Minus 10 joule. So delta U is negative. So gain or loss? Loss. Loss. Okay. So there is loss of potential energy. So potential energy is lost. Potential energy is lost. Okay, clear? So something is falling down. So potential energy is lost. Something is going up. Potential energy is gained. Okay, potential energy is gained. So we use this in our hydroelectric power also. So suppose there is a water is stored in a dam. So here turbines are there, correct? So here one pipe will be there, so it will rotate the turbine. Turbine is going very fast. So what energy is converted into what energy? Potential energy of water is converted into kinetic energy. Then kinetic energy of turbine is converted into electricity. Electricity, correct? So understood? So potential energy of water converted into kinetic energy of turbine, then turbine kinetic energy converted into electric energy. So there is a saying also, energy is neither created nor be destroyed, but one form of energy is converted into other form of energy. Okay, clear? So one good example of this. Okay, let's start spring. Again, let's come back to spring. Just 5 more minutes. Spring. So for spring potential energy, how will you find the formula? Spring potential energy. So work done by spring minus of this is equal to change in potential energy. So when spring is relaxed, what is the potential energy? 0. We assume when spring is relaxed, natural state, in natural state, spring is relaxed, it will not do anything. So what is the energy? 0. Now I am elongating it. Now you elongate it. By what amount you are elongating it? What is the elongation? X. So tell me, what is the spring force? How much is the spring force? Tell me, you know the formula. Tell me, what is the spring force? Minus k by 2 x2 square minus x1 square. So minus k by 2 x square. This is the work done by spring. Now what is u initial? 0. Now I want u final. I want to calculate u final. Now use this formula. Now delta u is minus ws. So what is delta u? U final minus u initial. So u minus 0 is equal to minus ws. And what is ws? Minus k by 2 x square. So what is the delta u? What is u minus 0 means u. So how much is u? Correct. Half k x square. So u is equal to half k x square. So this is the formula for potential energy. Okay, clear? Understood? So suppose spring is there, natural state. Natural state, what is the potential energy? 0. If elongation is x, then what is the potential energy of a spring? Half k x square. If compression is x, then also same formula. Okay. Suppose the same spring you are compressing. Now the same spring you are compressing x compression. Then again same formula you will get. So what is the potential energy? Half k x square. So whether compression is there or elongation is there, formula is same. Okay, understood? Now, what is the formula for f? Kx. F equal to kx. So what is x? What is x? F by k. So what is the formula for potential energy? K by 2 x square. F square by k square. So what is u? K cancel. F square by 2k. Okay. So note down. So just two numericals. K is equal to 200 Newton per meter. Spring is elongated by force of 50 Newton, force of 50 Newton, find potential energy. Spring is elongated. Now spring is elongated by a force because we need force. Spring cannot elongate by itself. You have to exert force. So what force you are exerting? 50 Newton. Calculate spring potential energy. Which formula you will use? Half kx square or F square by 2x? What is given here? In this question, what is given? X or F? F is given. So use this formula. Okay, solve. And second question. K is equal to 400 Newton per meter. Spring is compressed. Spring is compressed by 20 centimeter. Find spring potential energy. Find potential energy stored in spring. Find spring potential energy. Okay, clear? So memorize the formula. The potential energy of a spring, half kx square. So what is the what formula you will use for question number 2? Half kx square. What formula you will use for question number 1? Half f square by k. Okay, calculate. Tell me your answer. Question number 1. What is the answer? Joule. How much joule? 6 point. Okay. So 50 square by 2 into 200. So 2500. 2500 by 400. Okay. 100 cancel. 25 by 4. 6.25 joule. Very good. 6.25 joule. Okay. Next, half kx square. X you convert in meter. How much in meter? 0.2. 0.2 meter. Okay. 20 into 10 raised to minus 2 meter. So half k. K is 400. X square. 0.2 square. What is your answer? Tell me final answer. Tell me answer. Calculate. What is your answer? Tell me. 8. Okay, 8. Correct. So 200 into 0.04. So give this 100 to this. Decimal will be gone. So 2 into 4. Answer is 8. Okay, 8 joule. Okay, clear? Okay, done. We'll continue. Yeah, the spring we'll continue next class.